CrashLoopBackOff signifies the container exited, Kubernetes is restarting it, and the backoff delay is increasing. The non-zero exit code is the primary indicator of failure. Immediately execute kubectl get pods, noting the restarts count. If the count increments rapidly, the failure is deterministic and immediate. The first step is always kubectl describe pod, followed by the pod name. Focus on the status field and the last state section. This reveals the actual termination reason, often container creating or error, and the precise exit code that initiated the loop. This initial triage isolates the failure type, application error versus infrastructure misconfiguration, saving 90% of debugging time. After describing the pod, scroll to the Events section. Events provide a chronological history of Kubernetes actions related to the pod lifecycle. Look for specific warnings like failed sync or backoff. A common event is failed to create container, which points towards issues with the container runtime or image pulling, although image pull backoff is a distinct status. If the container successfully starts but immediately fails, the event log will show started container followed immediately by killing container. This sequence confirms the application process itself terminated unexpectedly. Analyze the message associated with the termination to identify resource limits, security context violations, or volume mounting failures. Out-of-memory killed, or OOMKilled, is a frequent cause of CLBO, indicated by the termination reason OOMKilled in the last state section. This means the container exceeded its defined memory limit, and the kernel terminated the process. To confirm, check the resource requests and limits defined in the deployment manifest. If the application requires 256 megabytes of memory, but the limit is set to 128 megabytes, the container will be killed under load. Increase the memory limit to accommodate peak usage, or profile the application to reduce its memory footprint. If the CPU limit is too restrictive, the application might fail to initialize within the startup period, leading to a restart loop, although this is less common than OOMKilled. Misconfigured config maps or secrets often result in application startup failure, triggering CLBO. If the application relies on environment variables injected from a config map, verify the key names exactly match the application's expectation. A missing or misspelled key results in a null value, causing the application to crash during initialization. Use kubectl get config map or kubectl get secret, followed by the name to inspect the data payload. Ensure the deployment volume mounts the config map or secret correctly if files are being used instead of environment variables. If the secret is missing or inaccessible due to role-based access control restrictions, the pod will often remain in pending or container creating, but if the mount fails after starting, CLBO occurs. A frequent CLBO cause is an incorrect container entry point or command definition in the deployment manifest. If the image uses a shell script as its entry point, ensure that script has executable permissions set within the Docker file. Use kubectl logs pod name -previous to confirm if the container failed before executing the main application process. If the container immediately exits with exit code 127, the shell cannot find the specified executable path. Verify the image tag is correct and accessible. An image pull backoff often precedes CLBO if the registry authentication fails, but a subtle entry point error causes CLBO directly after a successful pull. Always test the image locally using Docker run before deploying to the cluster if entry point modifications were recently applied.
If the pod requires persistent storage, a failure to bind the persistent volume claim can cause CLBO. If the application attempts to write data to a volume that is not yet mounted or is mounted read-only, the process terminates. Check the persistent volume claim status using kubectl get pbc. If the status is pending, the underlying persistent volume provisioner failed to allocate storage. If the persistent volume claim is bound, inspect the pod's volume mounts to ensure the correct path is exposed inside the container. If the application requires exclusive access, verify the access mode is read-write once. Incorrect file system permissions on the mounted volume are also a common failure point, requiring a security context adjustment in the pod specification. Liveness probes determine if a container needs to be restarted. An overly aggressive or incorrectly configured liveness probe will trigger CLBO even if the application is fundamentally healthy. If the initial delay is too short, the probe checks the application before it has finished initializing, causing a false failure. Increase the initial delay seconds parameter to allow sufficient startup time. If the failure threshold is too low, transient network issues or momentary high load can trigger a restart. Ensure the probe endpoint is lightweight and returns a 200 status code quickly. If the probe uses an exec command, verify the command path is correct and the exit code is 0 upon success. The most direct way to diagnose an application crash is by reviewing the logs from the container that just failed. Use the command kubectl logs podname -previous. This retrieves the standard output and standard error streams from the terminated container instance. Look for stack traces, unhandled exceptions, or specific error messages indicating why the application process exited. If the logs are empty, the container likely failed before the application process could write any output, pointing back to Entrypoint issues or immediate resource exhaustion. If the logs show a graceful shutdown message, the issue might be an external signal or a misinterpretation of the exit code. For complex CLBO scenarios where logs are insufficient, use ephemeral containers for live debugging. Ephemeral containers allow you to attach a temporary container, often running a debugging image like BusyBox or a specialized toolset, to a running pod. Execute kubectl debug podname -image -debug image -target -failing container. This allows you to inspect the file system, check network connectivity, and run diagnostic tools within the pod's namespace without restarting the failing container. Use this technique to verify environment variables, check file permissions, and manually execute the container's Entrypoint command to replicate the failure condition interactively. A senior engineer approaches CLBO systematically. First, check the exit code and termination reason via kubectl describe. Second, review the event section for infrastructure warnings. Third, analyze previous logs for application exceptions. Fourth, validate resource limits against OOMKilled events. Fifth, confirm ConfigMap and secret injection integrity. If the issue persists, use ephemeral containers to isolate the failure environment. Always document the specific exit code and the corresponding fix. This structured approach ensures that the root cause is identified quickly, preventing repetitive troubleshooting and improving overall system reliability.